Hello all. Our today's topic is exceptions and interrupts. That is this is your second chapter from the unit 4. So, before starting, we will go through what is the interrupt, what is the exceptions exactly. So, interrupts and exceptions are special kind of control transfer. They work somewhat like unprogrammed calls. What does that means? Interrupts. When your interrupt occurs, then processor has to stop its current execution and it will serve to your interrupt first and then will resume its regular task. Means what? Your exceptions and interrupts can alter the normal program flow to handle the external events or to handle the interrupts. For example, when we press any key to your keyboard, it is one kind of interrupt to the processor. The processor serves that interrupt and then continues its regular working. In short, we can say that the formal definition for the interrupt, the external asynchronous input applied to the microprocessor is called as interrupt. Interrupt is any kind of interrupt like hardware interrupt or software interrupt. When your processor is in execution and at the same time the particular IO peripheral device is waiting for the access, then the processor has to serve the device request first and then it will resume its regular task. So the interrupt can suspend the normal processor program execution and get itself served first. In short, for your convenience, you just keep it into mind. Interrupts are like serve me first. See, remember this phrase, interrupts are like serve me first. Now, the interrupts may be generated by internal chip operations or may be provided by external sources. So, there are some sources for the interrupt that your 80386 provides. Mainly, there are three kind of interrupt sources, namely hardware interrupt, software interrupt and error conditions. Hardware interrupt is further divided into non-maskable interrupt and interrupt. And software interrupt is your programming error or programming exception ranging from the interrupt 0 to 255 pin numbers. And error condition means any kind of error like divide by 0. For example, if your processor is executing one particular program and in that program by mistakenly it founds the statement or the program instruction like divide by 0. As we all know, when we divide any number by 0, then the answer will be infinity. But instead of showing the infinity option, your processor will generate the exception or error, that is divide by 0 error. Got it? Now, how to identify the interrupt? Interrupt can be identified by when the microprocessor is executing a program and if a user wants service to a IO device, then an external asynchronous input would inform the microprocessor, that is, it should complete the execution of current instruction and then serve the interrupt, and again it will fetch a new routine that will service the requesting IO device. Once the IO device is serviced, then the microprocessor resumes operation from the point whenever it had stopped. Now, you just have to remember 3 points in this, how to identify the interrupts. Okay. So, remember in the form of example, when interrupt occurs. Suppose at very first 3 steps, at very first your processor is executing some particular instruction. So, when second step is interrupt occur, then third step is processor has to stop and then service to the interrupt. And next step is after servicing interrupt, processor will resume or it will continue its normal execution. This is how we can identify the interrupts. On the priority basis, always we are serving the interrupt request first. Now, as I told you, hardware interrupt is divided into 2 parts, non-maskable interrupt and interrupt. Now, what is non-maskable interrupt? In hardware interrupt, as we are saying, hardware interrupts are the asynchronous interrupt or the interrupts generated by the external events. Underline this point, the interrupts generated by the external events. The means what? Physical pins are provided in the chip. These interrupts are generated by changing the logic levels on the 80386 interrupt pin. Now, our 80386 is having 2 interrupt pins, namely NMI, that is non-maskable interrupt, and second one is INTR, that is interrupt pin. Now, what is NMI or non-maskable interrupt? The microprocessor has to service this interrupt. It cannot avoid it. Means this interrupt cannot be disabled. This is having very high priority. Remember this. This interrupt always causes an interrupt sequence to be executed. Now, what is second one is in INTR pin, interrupt pin. This is maskable interrupt, means processor can mask this interrupt. It can be enabled and disabled using the 2 instructions. Remember, this INTR interrupt can be enabled or disabled with the help of 2 instructions. First one is your CLI and second one is STI. CLI is your clear interrupt and STI is store instruction. Now, if we want more number of interrupts to be processed, then we assign the priority to the interrupts. We are having next topic, our priority among the interrupts. We'll see it later on. These are the types of your hardware interrupt. Now, second source of the interrupt we are having, that is software interrupt. Now, software interrupt are generated directly by the program, or it is generated directly by executing the program. The int instruction of the 80386 can be used to do one of the 256 interrupts. Means what? Software interrupt can be generated from 0 to 255 interrupt type. This interrupt is specified by the number as a part of instruction. For example, int 0 instruction can be used to send execution to a divide by 0. As I told you the example, divide by 0 error, it is denoted by the instruction int 0. Means this is the divide by 0 error. Now the software interrupt, we can say that the software interrupt are same as your exceptions. Now exceptions are the programming errors or any anomalous conditions that must be handled by the kernel. Got it? The difference in between interrupts and the exceptions. Interrupts are generally hardware type of interrupts generated by the external events, whereas the exceptions are caused by your programming errors. Now, like interrupt, your exceptions is also having some sources. Like exceptions are classified into 3 parts, namely faults, traps and abort. Now we will see one by one what is fault, what is abort and what is trap. Now, as I told you, exceptions are generated by the internal events, while interrupts are generated by the external events. Mark this point. I am repeating it again. Exceptions are generated by internal events, means by your programming errors, and interrupts are generated by the external events. Now, exceptions are divided into 3 parts: faults, trap and abort. Now, very first, the fault. What is fault? These are the exceptions that are detected and serviced before the execution of the faulting instruction. Remember this, it is serviced and detected before the execution of the faulting instruction. A fault would occur in a virtual memory system. The operating system would fetch the page or segment from the disk, right? And then 80386 would restart the instructions. For example, instruction 0, instruction 5, int 6, likewise. In short, your 80386 will execute the instruction that created the fault after completion of the exception handling software. This is all about your fault. A second type of exception is your trap. A trap. These are exceptions that are reported immediately after the execution of the instruction that caused the problem. Now remember the difference in between fault and trap. Fault occurs before the execution of the faulting instruction, whereas your trap reported after the execution of the faulty instruction. This is the difference in between fault and trap. Now traps are user defined interrupts. For example, int 2, int 3 and int 4. These are the numbers or interrupt or instructions for the trap. The instruction that caused the trap cannot be restarted, whereas in fault we can restart the instruction, but in trap we cannot restart the instruction. And the last source or last type of your exception is abort. Now what is abort? These are again the exceptions which do not permit the precise location of the instruction, causing an exception to be determined. Do not permit the precise location of the instruction to be determined. Aborts are used to report serve error such as hardware error or illegal values in the table. The program with aborts must be terminated, must be ended. Example of the abort is INT 8, interrupt 8 and interrupt 9. Now, our next topic is priority among simultaneous interrupts and exception. Now, all of you might be clear about the interrupts and exceptions, type of the interrupt, type of the exception. So, moving forward, our next point is priority among simultaneous interrupts and exceptions. Now, what if when two or more interrupts occur at the same time, how processor will serve it? This is the question again. When this happens, two or more interrupts occur at the same time, then the higher priority interrupt will be served first. The higher priority interrupt will be served first, and then the next highest priority interrupt will be served, and at the last lower priority interrupt are made pending, or sometimes these lower priority interrupts are discarded by the processor. We are having the table which shows the priority of the interrupt. Suppose the interrupts are like divide error, into, false, trap and instruction. These are the highest priority instructions, highest priority interrupt. Processor has to serve it first, and after that your debug faults and traps, your non-maskable interrupts is having next highest priority. The INTR is at the lowest, and single step is sometime this single step interrupt will be aborted or discarded by the processor. In this way, processor decides the priority of the interrupts and exceptions and accordingly serve them. Now, our next topic is enabling and disabling interrupts. The processor services interrupts and exceptions only between the end of one instruction and the beginning of the next instruction, right? As we study before, the processor, suppose processor is executing particular program, interrupt occurred, it will suspend the execution of that program, serve the interrupt. After serving the interrupt, it will again resume the next instruction. Likewise, when the certain condition and flag settings cause the processor to inhibit certain interrupt and exception at instruction boundaries. Now, the conditions like NMI masks NMI. Means what? Non-maskable interrupt masks non-maskable interrupt. In that, if the microprocessor is servicing an NMI interrupt, the processor neglects the interrupt that occur on the NMI pin till the I return instruction is executed. Getting this point? If processor is serving your NMI, as we are having NMI is highest priority. See this table. Here we are showing after divide error and false trap, the highest priority interrupt is your NMI. When processor is serving your NMI and again the interrupt occurred at the NMI pin, then that will be neglected by the processor. Now second condition is IF mask INTR. Interrupt flag masks INTR. The external interrupts that are controlled through the INTR pin, right, means this is your hardware interrupt. External interrupt means hardware interrupt. For that we are having INTR pin, right? Then these are controlled by your interrupt flag or IF flag. Remember IF flag we have seen in the flag register in first and second unit. Here if your interrupt flag is 1, then the interrupts are enabled. But if your IF is 0, then interrupts are disabled. Now for that we are having two instructions, STI and CLI, means set flag and clear flag instructions. These instructions can be executed only if your CPL is less than or equal to IOPL, means current privilege level is less than or equal to IOPL instruction. When this condition is not satisfied, the exception will be generated. We have seen in your third unit CPL, that is current privilege level. The highest CPL is your PL0, that means kernel level. Now the third condition is RF masks debug faults. The debug faults are recognized to the RF bit in the E flag register. Again remember the RF bit in the E flag register, we have already seen in your first and second unit. For an instruction, the number of times instruction is restarted, the debug fault is raised only once. Debug fault is raised only once. This is all about masking the debug fault. Now the last condition is move or pop to SS mask interrupt and exception. For example, the instructions like move SS comma accumulator, move ESP stack pointer comma stack pop. These are used for modifying the stack segment. If after your stack segment is modified but stack pointer is not an interrupt or exception is processed, the stack pointer content during the interrupt service routine. Hence we can say that to avoid this condition, after move SS comma AX and pop SS instruction, the 80386DX prevents the INTR, NMI, and single step trap debug instructions. This is how we can enable or disable the interrupts. These are the conditions for that. Thank you.